Hello APC Mechanics students, today we will solve the past paper FRQ 2006 exercise 3. A thin hoop of mass capital M and radius capital R and rotational inertia m r square is released from rest. Then initially we don't have any kinetic energy from the top of the ramp of length L above. The ramp makes an angle theta with respect to a horizontal tabletop to which the ramp is fixed. The table is a height h above the floor. Assume that the hoop rolls without slipping. Then both variables of motion, rotational and translation, are related to each other. Down the ramp and across the table, express all algebraic answers in terms of the given quantities and fundamental constants, basically m, r, l, h, and theta. Then derive an expression for the acceleration of the center of mass of the hoop as it rolls down the ramp, and we know that we can solve this part using two strategies, either Newton's second law or using conservation of energy. But the thing is that if we're gonna use the conservation of energy, that would allow us to determine the speed before the acceleration. And you notice carefully for the order of the parts. In part B, they're gonna ask us for the speed. So it's better for A to determine that using Newton's second law in order to determine the acceleration. Then in part B, the speed can be deduced either via calculus or kinematics. Now, in order to determine the acceleration, we need to utilize the hoop through a rigid body diagram. So basically, this is the ramp. And let me say that this is the hoop. And now what are the forces that are acting on the hoop? We have the pull of gravity from the center. Now notice that because it's a rigid body diagram, we need to represent the forces from the point of application correctly. That would be the pull of gravity. And we have the normal push that acts on the point of contact between the hoop and the ramp. That's the normal push. And we have the friction that acts also at the point of contact, but opposite to the direction of motion of the ball. So that would be static friction. Why here in this case we have static friction? Simply because it's the force that provides a grip in order for the motion to be without slipping. And now we're gonna apply Newton's second law for rotation. So apply Newton's second law for rotation. And here we need to specify the pivot point that we're interested in working in. So, for example, if you consider the pivot point, which is basically the point of contact, then we can directly eliminate the friction force and the normal push, and only the pull of gravity would be providing torque for the rolling hoop. So about the point of contact. So we're gonna say that the net torque is equal to I multiplied by alpha, but notice here carefully, what does this I represent? Since our pivot point is this, then I would be dictated by the parallel axis theorem. Then we need to add a moment of inertia for mr square in order to compensate for the shift from this point to this point. Now the different forces that are acting on the rigid body, we have the pull of gravity plus the friction, or the normal push plus the friction. That would be equal to the moment of inertia, which is basically mr square about the center, plus the mass times the shift, r to the power of 2, multiplied by alpha. Now that would be 0, because the line of action of these forces passes through the pivot. Now the torque produced by gravity, now here let me state carefully that this is the angle, so theta here. And we know that if this is the radial direction and that's the tangential direction, if this is the angle theta, then that would be pi by 2 minus theta. Then the projection of the pull of gravity along the tangential would be cosine pi by 2 minus theta, which is sine theta. And we're always familiar that the pull of gravity negotiate with the sine and not the cosine if the theta is the angle of the ramp. So that would be mg multiplied by the distance from the point of contact to the point of application of the force, which is r, multiplied by sine theta, equals to 2mr squared. But because we're interested in the acceleration linear, not angular, we know that they are related to each other via alpha is equal to a divided by r. So that would be a divided by r. Now r cancels with the power 2, this r cancels with r, and m cancels with m, and the acceleration in this case is given by half g sine theta. And this is anticipated. Why? Because we know that this can be directly guessed from the fact that for bodies rolling without slipping, the acceleration is given by g sine theta divided by a term which is given by 1 plus ICM divided by mr squared. And because the moment of inertia around the center of mass is given by mr squared, so this overall would be 2, and that would be given by half g sine theta. Now, after we have determined that the linear acceleration of the hoop is given by half g sine theta, now we can say that we can use kinematics basically. So v square x is equal to v square x0 plus 2ax delta x, initially starting from less, so that would be 0. Now we will call this speed to be v. Now delta x, in this case, what does delta x? Delta x is the distance along which the hoop travels, which is basically L. So that would be L. And we have determined the acceleration to be half g sine theta. So that would be given by, let me say that the speed is given by v square equals to 2 into half g sine theta multiplied by L, which is basically g sine theta multiplied by L. Then the speed is given by the square root of gl sine theta. And remember that in such type of problems, under the influence of gravity, we anticipate that the speed is gonna be given by a coefficient multiplied by gl, and in this case the coefficient is given by sine theta. Now in part C, derive an expression for the horizontal distance from the edge of the table to where the loop lands on the floor. The hoop lands on the floor, and this can be utilized by kinematics. If the hoop at this point possesses only horizontal velocity, then we can say that then x is given by x0 plus v0 cosine theta t, because the launching angle is 0, which makes this to be 1, and we can always set our origin. And let me say that the horizontal distance is capital D, and v0 is basically v that we have determined in the previous part. Then d would be given by vt, and in order to determine t, because remember that our answer should be expressed in terms of the given, not time. Time can be determined by referring to the vertical position. We know that y is equal to y0 plus v0 sine theta t minus half gt squared if our positive direction is up. That would be 0, and because our positive direction is up, the vertical position would be negative h. Theta is 0, which makes this component to be 0. Then what do we have here? We have minus h equals to minus half gt squared, and minus with minus would cancel, which means that t is given by the square root of 2h divided by g. Then the horizontal distance t would be given by v. V is given by radical gl sine theta from the previous part, multiplied by radical 2h over g. G with g cancel, and the horizontal distance in this case is given by the square root 2hl sine theta. Now suppose that the hoop is now replaced by a disk. So what's the difference between the hoop and the disk? Both they are of the same mass m and the radius r, but the only difference is how this mass is being distributed along the shape of the body. We know that in this case, because the mass for the hoop is being distributed along the rim, the hoop is more inertial than the disk. The moment of inertia of the disk actually is given by half mr squared, and upon rolling without slipping, the disk, because it is less inertial, it will gain more linear speed, and it will gain less angular speed. So let me repeat again, because the disk is less inertial than the hoop, then it will gain more linear speed and less angular speed. How will the distance from the edge of the table to where the disk lands on the floor compare with the distance determined in part C for the hoop? Now, as we were saying that if the hoop is now replaced by a disk, this disk at this point will have more linear speed, and we know that the horizontal distance is given by Vt. Now T actually is given by the radical of 2h over g, the vertical, and this is determined from the vertical component, and it doesn't depend on V. However, the horizontal distance depends. As V increases, D increases. And what does this V represent? This is the linear speed. Because the disk will possess at this point more linear speed, then it will cover more horizontal distance. Then let me say the following. So that would be greater than, since the disk has a moment of inertia less than that of the hoop, then the linear speed of the disk at the bottom of the ramp is greater than the disk will cover a larger horizontal distance than that of the hoop. And that's it for me in this video, guys. See you soon in a new one.